Today we're doing the topic 6 for remediation, all about exponential functions. Section 6.0, our instructions are to simplify. We're going to use our exponent properties to help us do that. So the first thing for our first problem that we need to recognize is that we're multiplying two terms together. And when we multiply two terms together, we get to multiply their coefficients. 3 times 4 is 12. And then their variable, because they have the same variable, they get to stay the same. So our x is just going to come down in our problem. The one thing that we're adding, the new bit of material, when we have two different exponents and we multiply them together, we are going to add them. So we're going to take 3 plus 8 equals 11, and that gets to become our new exponent, 2x to the 11th power. So whenever we see multiplication, remember we add our exponents. Now, our second problem is one that has a set of parentheses. And we know when we do parentheses, or when we see parentheses in our problem, that's the thing we need to deal with first. And on the outside of our parentheses, we have this exponent of 3. We kind of get to apply or distribute this 3 to every single term in our problem. So my 3 gets raised to the power of 3. My 2 gets raised to the power, or my x to the negative 2 power gets raised to the power of 3. And the property that we're following along with here is multiplication. So we're going to do 2 times negative 3. Y to the 4th gets to be multiplied by 3 as well. And x to the 3rd gets to be multiplied by that 3 as well. So each of my 4 terms gets this exponent of 3. And now we get to go ahead and simplify. 3 squared is 3 times 3 times 3, which is 27. Negative 2 times 3 is negative 6. 4 times 3 is 12. And 3 times 3 is 9. Now, the one last thing in our problem, we're not fully simplified until we just see one instance of every variable. But here we have x to the 6th power, and we have an x to the 9th power. This is our multiplication process or property that we used in our last problem. When I'm multiplying two things together, I get to add their exponents. So negative 6 plus 9 is positive 3. So I know I'm going to have x to the 3rd power in my answer. Nothing's going to change about my 27, so I just get to bring it down. And then nothing's going to change about y to the 12th. So my final answer is this guy right here. And then we're going to apply that same property when we have parentheses. But the cool thing about our fractions is we apply the 3 to the top of the fraction and to the bottom of our fraction as well. So that 3 gets to go on the top with the x and the bottom with the y, and that's actually our final answer. I'm not going to rewrite it. X to the 3rd, y to the 3rd. Now, sometimes we will be given problems where we're going to have to use these properties, which is why we needed to start with them first. But we can take a radical in a problem and convert it to be an exponential form. So there is a small process that we're going to follow. One thing we need to remember first is that when we're taking the square root of a problem, there's a little invisible number here of 2. The square root implies you're taking the second root of something. So we're going to take the base of the exponent, which is 3x, and it's grouped together in parentheses, so we're going to keep it grouped together in our parentheses. And to write this in exponential form, we're going to take this number 2, we call that the index, goes on the bottom, and then this exponent goes on the top. This is the same thing as 3x to the 4 over 2 power. Now, in math, whenever we can simplify, we want to. 4 divided by 2 is 2, which means that this is 3x squared. And using our properties of exponents that we did up above, remember that this 2 gets to be applied to each of these terms. So that's going to be 3 squared times x squared, which is going to simplify to be 9x squared. 3 squared is 9, x squared just gets to stay the same. We can do the same thing in our next problem here. Our index is 3, and then the power of my problem, I'm actually going to just separate this into 2 separate problems. So we can kind of do it like we did our last problem. That's the third root of x to the 6th power times the third root of y to the 12th power. And let's go ahead and write an exponential form. That's going to be x to the 6 divided by 3 times y to the 12 divided by 3. And we can simplify those fractions, right? 6 divided by 3 is 2, so I have x squared. 12 divided by 3 is 4, so I have y to the 4th power. So I just broke them up into 2 separate problems there and simplified those fractions to get my final answer. Now, we went from a radical to an exponent. Now we're going to be given an exponent, and we're going to write this expression in radical form. So it's kind of like this one that we did here, but backwards. The base of my exponent, what's grouped together, that 7x, gets to go underneath of the radical. And then I just need to figure out where my 2 and my 3 are going to go. I always remember that the denominator becomes our index. So the 3 at the bottom goes here, and the numerator, the 2, gets to go as the exponent of our problem. So really it was this problem, but we did it backwards here. And then this last one, what we're going to do is just use a bunch of our properties of exponents to simplify this. We've got this written in exponential form right up here at the top. We can write it in radical form if we want to. I like leaving things in exponential form. So I'm going to take this 1/3 and I'm going to apply it to both of my 2 terms in my problem. Y to the 9th times 1/3. That's my property of exponent there. Y to the 12th times 1/3. And that's all I can do in my numerator right now. So I'm going to go ahead and simplify that one step further. 1/3 times 9 is just 3. So that's x to the 3rd power. And then 12 times 1/3 is 4. So that would be y to the 4th. And this is still getting divided by our denominator, which was x squared y to the 3rd. And this is a property of exponents we haven't talked about yet, which is the division one. Whenever I have a fraction in my problem where I'm dividing, I take my exponents of my like terms and I subtract them. 3 minus 2 is 1, so I'm going to be left with x to the 1st power. And we have to do the same thing with our y terms. We have 4 and 3. 4 minus 3 is 1, so I'll be left with y to the 1st power as well. You also can think about this in like an expanded form. That means that I have 3x's divided by 2x's. So if I cancel out the terms, I'm left with 1x on the top, which is why we got x to the 1st power. And then we can do the same thing with the y's. We had 4 y's on the top, 3 y's on the bottom. You can cross out and be left with 1 y at the top. So that's another way to think about it. That's kind of why the exponent rules work the way that they do. So now we're going to flip over and we're going to write and graph an exponential function. So the first thing we want to do is identify the a and the b value. A is this number out in front of our parentheses. So A is going to be 2. And B is the number inside the parentheses, which is 1/2. And this is what we call the growth/decay factor. And this lets me know whether it's growth, decay, or neither. If it is a fraction, then it's decay. I'm thinking it's decreasing, it's getting smaller. If it was a whole number, it would have been growth. But in this case, it's the decay factor. Now, to find or fill in the rest of this table to get the points that we can graph, I am going to use my calculator. So this is something that you can use on the Desmos calculator on the computer, or if you have a calculator handy. I'm going to take my equation 2 times 1/2. And I'm just changing the exponent every time. The first one I want to simplify for is when x is -2, and it tells me that is 8. I'm going to copy this down, and I'm just going to change this to a -1. That tells me that it's 4. I'm going to change this to a 0. That is 2. I'm going to change it to a 1. It's 1. And then I'm going to change it to a 2, which is 1/2. So I've got my 5 points there. Notice that we said the decay factor was 1/2, which means as we change our y values, we're dividing by 2 every time. So that's kind of like the pattern that we can see on the table. And I'm just going to plot these points. -2 up 8, -1 up 4, over 0 up 2, my y-intercept, over 1 up 1, over 2 1/2. One of the characteristics of an exponential function is that it's going to get smaller and smaller and smaller here, but it's never going to cross the x-axis. So we can't draw this very well, but if we graphed it on Desmos, we could see this side's going to go up forever, but this side's going to go down, and it's never going to cross the x-axis. It's going to look something like this. And we like exponential functions because they do model real-life situations, which is what we've got going on in example 6.3. So this says a population of endangered birds is decreasing at a rate of 3% per year. In 2010, there are about 200,000 of these birds, and we're going to answer some questions here. Does this model first represent growth or decay? Well, my keyword here is that it's decreasing. So when something's decreasing at a rate, we're going to say it's decay. What was the initial amount, the starting amount of these birds? I guess we're starting in 2010. There were 200,000. What is the growth/decay rate? Well, we know it's decay, right? Because they told us it's decreasing. This is 3%, but when we do 3% in an equation or a problem, we have to convert that into a decimal, which is the same thing as 3 divided by 100, which is 0.03. The growth or decay factor is 1 minus the rate. So in our case, because it's decay, it's minus. In our case, it would be 1 minus 0.03, which is the same thing as 0.97. And then we want to write an exponential equation that represents the situation. When we do this, it's y equals a times b to the x power, where the initial amount is a, and our decay factor is b. So we kind of already pieced together this information, but we're going to make it a little bit more formal. This is y equals 200,000 times, let me scoot this over, times 0.97 to the x power. And it's asking us how many birds will be in the year 2118. So in how many years would that be? 108 years. That is going to be a good point to talk about. We're starting in the year 2010, and we want to find the population in 2118. So we want to calculate how many years is going to pass in that time frame. So I'm going to subtract those two numbers, and I get 108. I just said that, but that's important to note because we're going to use our equation to help us find it. That's 200,000 times 0.97 raised to the 108 power. That becomes our exponent, and that's something I can type in my calculator. 200,000 times 0.97 raised to the 108 power. So there will be around 7,453.8 birds. I'm going to just round because you can't have 0.8 of a bird. So I'm going to round to 7,453 birds. And then we've kind of got the same type of problem going on for our next one right here, except where we didn't have to come up with the equation ourselves. We just need to use our equation. So when we're given this x value of 10, that just means we plug that into our equation. What I'm going to type in my calculator is 25 times 1.25 raised to the 10th power. This is an example of growth because the base of my exponent is greater than 1. It's not a fraction. So we should expect our number to get bigger. So this time, it doesn't tell me what to round to. I'm going to round to the nearest 10th. So the 3 is going to leave my 8 alone. My answer is going to be 232.8 if I evaluate my problem. And then last but not least, our geometric sequences. Our explicit formula is going to require us to figure out a few things about our problem. First, we need to figure out how my values here are changing. What number am I multiplying by each time to go from one to the next? Well, I know my numbers are decreasing. So we can think about that as like 81 divided by 3 is 27, and dividing by 3 gives me 9. So I can think about this as dividing by 3. But when we're talking about a geometric sequence, we always want to write it in terms of multiplication. So this is the same thing as multiplying by 1/3. So this is going to be my decay rate, right? 1/3, that's the rate that my problem is decreasing by. And remember, when we write our explicit formula or in a geometric sequence, we're going to say AN equals A1 times D. I guess we're going to call this D to the nth term. A1 represents our first term in our equation, so that's going to be 81. D is our rate of increase or decrease, which is 1/3 raised to the nth power. This equation is going to help me find any term that I care about. We call this the explicit formula, and we can use it in our problem to find the sixth term. What that means is I'm just going to take 81 times 1/3, and I'm going to raise that to the sixth power. So the 6 gets to get plugged into my exponent this time. And I'm going to use my calculator here. 81 times 1/3 to the sixth power. So my answer is 1/9. And that should make sense, right? Because my numbers were decreasing as I was going along. So my number was getting smaller and smaller each time. That's going to be our last problem for today. Now y'all are ready to take your remediation quiz.